Good morning. Manohar, whether the screen is visible? Manohar. Aradhana, whether the screen is visible?
Yes, sir.
Okay. The last class we were solving the problem. What was the fuel cost for option 1? Option 1 was unit 1 and unit 3 committed. The dispatch was 380.136 plus 419.8621. The total operating cost was 8970.2 dollars per hour. Dollars per hour. Option 2, unit 1, unit 2, and unit 3 committed. What's the dispatch? Laura?
So for P1,
Hmm.
325.4, 318.
325.4318. Huh?
Yes, sir.
Alright. For unit 2,
99.8208.
99.8208. For unit 3,
374.731.
374.73. Yeah. Whether all the constraints are justified?
Yes, sir.
Okay. What's the cost associated?
Uh, Total cost or separate costs, sir?
Total cost.
9,294.
9,000.
294.4283.
9,294.4283
83.
per hour. Okay. So this operating cost, we can say that this is the least operating cost. So this is the optimal unit commitment for that particular hour that we solve using the priority list method. When you want to solve for more number of hours using rearranged method, using a computer, we will be able to solve it. We have to consider some other constraints as well. But if you keep on repeating it manually, it will be a tiresome exercise. So the concept is like this. When you want to implement rearranged for more number of hours, you can tailor the algorithm, discuss and use it. So now we are going to look into another example where we are just method is not about we will we have these three generators and we will be having 3 hours. We are going to find out the unit commitment schedule for these units. And you please note down the problem. Find unit commitment schedule for the system shown below. Write it and make a note of mistake. Manohar, have you noted the problem? Right, find optimal unit commitment schedule for the system having following units. Unit A, B, C are there. Each unit have a minimum limit and maximum limit. Each unit have a minimum uptime and minimum downtime. All the units have the no load loss as 0 and the marginal cost is in dollars per megawatt hour is being given and startup cost for each unit is given. If you want to start that unit, what will be the cost that is being given and initial status of the unit started. The initial status before hour number 1, only one generator was operating. A was on. Now the demand is for hour 1, demand is 150 megawatt. For hour 2, demand is 300 megawatt. Hour 3, the demand is 200 megawatt. Let's not consider about the reserve requirements now. Now we have to supply the demand considering the uptime and downtime constraint, Pmax and Pmin constraints by having minimum operational cost. So we have three units. Three units. Let us consider 000 is representing that the three units are in off state. 0 represents the unit is in off state, decommitted state. 1 represents the unit is committed state. Unit is in committed state. Now we have several combinations. One means all the generators are committed. 110 represents the generator 1 and 2 is committed, 3 is decommitted. Now, for the hour 1, 150 megawatt is the load, right? 50 megawatt is the load. Now, if you see P minimum that can be supplied and P maximum that can be supplied. So, I have summed up the minimum limits of all the three generators and written here. I have summed up maximum limits of all these three generators and written here. So all the three generators running, you can supply the power from 210 to 400 megawatt. Right? When first two generators are running, I have summed up the Pmin values for first generator and second generator and Pmax value for first generator and second generator. Here, some of minimum generation values for generator 1 and generator 2 is 200. Sum of maximum generation value at generator 1 and generator 2 is 350. Similarly, I have written all the possible minimum generation and maximum generation. Okay. Now, first hour demand is 150 megawatt. We have not considered losses. So whether this state 111 is feasible to supply 150 megawatt. Manohar, Prasanna Kumar, Vishnu,
Yes, sir.
whether the first combination 111 will be sufficient to supply 150 megawatt.
150
Whether
megawatts, sir.
feasible, 150 megawatt, whether there is a feasible state.
Yes, sir. 150 more than more. It can provide more than 150, sir.
More than 150, the minimum power that can be generated is
Yeah,
210
150, sir.
megawatt.
Yes,
Huh?
sir. Yes, sir.
Minimum power that can be generated is 210 megawatt. Now, whether this is a feasible state or infeasible state,
Feasible, sir.
right? Feasible. Minimum you can generate only 210 megawatt. You should generate. Now the demand is only 150 megawatt, right? What you will do with the rest 60 megawatts, right?
Yes, sir.
You cannot keep that 60 megawatt generated and do not consume. Frequency of your system will keep on increasing, right? Right?
Yes, sir.
When the need is 150 megawatt, you should not pump 210 megawatt into the grid, right? At that time, you should pump only 150 megawatt. So first solution is not feasible. First combination is not feasible. What about the second combination?
Yeah, 200, sir. More than 50 is more.
50 is more. So it is not feasible. Not feasible. With this combination also, it is not feasible.
Not feasible.
With this combination, whether it is feasible,
Feasible 150, sir. Required.
we require 150. So it is feasible.
Feasible.
Right? What about the next combination? This combination?
This 150 can provide, sir. This way.
150 we can provide. Minimum provided by this combination is 50. Maximum provided by this combination is 100.
100.
Our demand is 150.
Yes.
With this
No, not feasible.
not feasible. So it's not feasible. This fellow is this combination is also not feasible. This combination will always be not feasible. Okay. So
Yes, sir.
we have only these two combinations feasible. Okay. These two states as the feasible states. Now, for 300 megawatt, whether this combination is feasible, same Vishnu,
It can provide 300, sir.
300, yes, feasible. Okay, thank you, Vishnu. Okay. Nitin? Nitin? Nitin can call me later. Ilakya? Ilakya? Ilakya can call me later. Shravan?
So yes, sir.
Okay. Now
Sir.
with this combination, whether 300 megawatt we will be able to supply.
So which one? First one.
With this second one.
Yes, sir. Yes, sir.
Third one,
Yes, sir. Maximum.
fourth one.
No, sir.
No, we cannot. We won't be able to supply 300 megawatt from that combination. So the feasible combinations are the first three, and the rest are infeasible. So we have 3 feasible states and 3 infeasible states. Similarly, for the third hour, we will be having, we have 200 megawatt as the demand, The minimum limit here is 210 megawatt, so we cannot supply with this combination. Here the minimum is 200, maximum is 350, demand is 200. So this is a feasible state. 200 megawatt is within 160 and the 300, so this is a feasible state. And 200 megawatt is within 150 and 250 as well. So this is a feasible state. Here the maximum here the maximum is 150 megawatt. So it would be an infeasible state. Similarly, these two are also infeasible. So we have for the first hour there are two possible states. For the second hour there are three possible states, and for the third hour there are three possible states. Now we have initial state. We had something called the initial state given in the problem. Initial state of first generator was on, second generator was off, third generator was off. So initial state was 1, 0, 0. Okay. So now from this initial state 1, 0, 0, you can move to 1, 0, 0. That is the same state at hour number 1, and from that there were three possible states, right? In hour number 2 there were three possible states. Three possible states. So from hour 1 you could have gone to any of these two states. From any of these two states, you can go to any of these three states, right? And from any of these three states, for hour number 3, you can come to any of these three states, right? So that means that at hour number 0, first generator was off, second generator, first generator was on, second generator was off, third generator was off. Keeping first generator alone on, you could have supplied the demand required in hour number 1. Or else you could have turned off first generator and turned on second generator and third generator. And in that scenario also you could have supplied that demand in the first hour. Now, if you have not turned on or turned off any generator, you will be in this state. At the second hour, you can turn on the two remaining generators. First generator is alone on. These two remaining generators you can turn on and move to state 111. Okay, move to state 111, and you would have dispatched the generators and supplied the loads. On the other hand, from this state, you could have turned on the second generator. First generator was already running, second generator you can turn on to move from this state to this state. Alternatively, instead of turning on the second generator, you could have turned on the third generator and moved to this state. Now, we had told that there are some constraints. The minimum downtime of unit A considered. The minimum downtime. The minimum downtime of unit A was given as 3 hours, right? Unit B was given as 1 hour, unit C was 1 hour. if we go through this process, this path, then unit A is on here. In this state, unit A is off, right? Again, to move to any of these three states, unit 1 have to be turned on again. Unit 1 have to be turned on again. But unit 1 cannot be turned on before 3 hours of rest. If it is turning off, we should turn it off for 3 hours. So these three paths are infeasible. These three paths become infeasible. So we have drawn all the feasible paths, and we are neglecting the infeasible paths now. Then, if you consider the minimum uptime of the second unit, minimum uptime of the second unit is 2 hours. Now, at this point, second unit was off. Here, second unit is on. If you move to this point, again second unit is on. If you turn on unit number 2, you should maintain it in on state at least for 2 hours. So you are not able to justify that constraint now. So this is an infeasible path. This is an infeasible path. Similarly, if you want to go to this state as well, you have to turn off the second generator. So that also becomes an infeasible path. From this state to this state also, you have to turn off the second generator. Turn on the second generator, maintain it for running for 1 hour, and at the third hour, you again turn it off. So the dotted lines here represents that those paths are infeasible. So we have certain feasible paths only. So all the infeasible routes we have neglected. Now we retain only the feasible paths. So I am just giving names for all the states. State 1 is 100. State 100, I am naming it as 1. State 111, I am naming it as 4. Excuse me. 100, I am naming it as 1. 101, I am naming it as 2. 110, I am naming it as 3. 111, I am naming it as 4. Similarly, I am giving names for all the states. Now, we had these states. For each state, what is the demand also we know. Here we had a demand. What was the demand for the first state? Prisham? Pritham? Shravan? Shravan? So anyone can answer? Who have the answer?
So 150.
There was 150. For the second state and third state and fourth state, what's the demand?
101. 300.
300 for these states. The demand is
200.
200. So demand for the first state is 150. 2, 3 and 4 is 300. 5, 6 and 7 is 200. For the cost function, we were not given with a full cost function. We were given the marginal cost. Marginal cost means DCI. DCI by dPi generally will be equal to Vi plus 2 gamma I Pi, right? DCI by dPi is beta I plus 2 gamma I Pi. Here it's given in a single value, means the beta I value is given. So per megawatt cost is given, and it's obvious now that if you generate it in this particular generator, you are going to end up at the least cost. If you use this generator, the cost will slightly increase. And if you use this generator, the cost will further increase. So because the marginal cost, that is cost per megawatt hour, is 10 here, it's 12, and it's 20. It's in increasing order. So first you commit first generator, give first priority to that generator. If it is not possible to supply the load only with first generator, then you turn on the second generator, that is unit B. And if at all first generator and second generator cannot supply, then cannot supply the demand, then only we will be running on the third generator, because the marginal costs from the marginal cost itself, we can see that unit A is the least cost generator and unit C is the costliest generator. Now we have the load as 150. The 150 megawatt can be generated from unit A itself, and the marginal cost is 10. So the cost is 1,500. Next is 101. This is the status. You have to turn on first generator and the third generator. We are going to investigate whether this is coming out to be the P1. This is first generator, this is the third generator. First generator and third generator are on, second generator is on. Now, among first and third, first generator has the low marginal cost, that is 10. Third generator has marginal cost 20. So, load first generator till its maximum limit. 250 is the maximum limit for first generator. 250, and the demand is 300. The rest 50 is assigned to the third generator. Okay, rest 50 is assigned to the third generator. And if you calculate, the cost will be 3,500. Now, for this state 110, first generator is on, second generator is on, third generator is on. So, third generator value is 0. We have to dispatch the load between these two generators, unit A and unit B. Unit A's maximum demand, you can supply 250. It's the low cost unit. 250 you take it from that. The rest you take it from the unit B. Unit A is 250, unit B is 50. If you calculate the cost, it will be 3,100. 250 multiplied by 10 plus 50 multiplied by 12. 12 is the marginal cost. Now, we have all the generators turned on in this particular state 1, 1, 1. Now, this generator have a maximum demand of 250, maximum power that can be supplied as 250. It would have been economical if we have generated all the 250 megawatt from this particular fellow itself, but the state tells that unit B and unit C should be turned on. Right? Unit B and unit B and unit C should be turned on. Unit B's minimum limit is 50 megawatt, right? So 50 megawatt is applied here. Unit C's minimum limit is 10 megawatt. So 10 megawatt is applied. So the rest is being generated by the first generator, 240 megawatt. Now if you calculate the cost, it should be 240 multiplied by 10 plus 50 into 12 plus 10 into 20. So it should turn out to be 3,400. Similarly, all other states can also be dispatched. Priya, can you explain the values in this state?
State 6 is 101, So generate unit A and C is on. Total load is 200. It must be divided between unit A and C. C is we give the minimum P minimum as 10. So remaining 190 is given in unit A.
Oh, the remaining one of this unit. So, thank you. Now, all the states are dispatched. We have found out the economic dispatch for all the states. Now, if at all, instead of just giving the marginal cost, if a fuel cost function is being given with alpha i's, beta i's, and gamma i's, then you could have solved the economic dispatch problem for a particular state and found out the cost of fuel at each state. The fuel cost at each state is being found out now. Then we have to find out the transition costs. Now, for each state, we have given what is the fuel cost incurred. Okay, what is the fuel cost incurred at that particular state at that particular hour. So now this state 1 is 100, the initial state is 100. Then what should be the transitions cost from here to here? What should be the transition? What may be the transition cost from this state to this state? There is no transition cost. Your transition cost means startup and shutdown costs. Startup and shutdown costs. You are not starting up or shutting down anything, so the transition cost here is 0. Okay. Now, this state is 100. Preetham, what is state 2? What is the binary representation for state 2? Rohit? Savit? Kalishwari?
Sir,
What is the binary representation for state 2 as per the problem?
101.
101 is state 2, right? So, to move from state 1 to state 2, what we have to do? What we have to do?
We have to turn on 3, sir.
We have to turn on generator 3. What's the
Generator
turn
3.
on? What's the turn on cost for generator 3? Startup cost. What is the startup cost for generator 3?
$100, sir.
So $100. To move from state 1 to state 2, the transition cost is $100. Okay. What is state 3? What's the binary representation for state 3?
$110.
110. So move from state 1 to state 3. What we have to do?
We have to turn on second generator 2.
Second generator. What is the startup cost for second generator?
600, sir. $600, sir.
$600. Okay. So now,
Yes, sir.
what is state 4?
111.
111. To move from first state to fourth state, what we have to do?
Sir, what?
To move from first state to fourth state, what we have to do?
3 and 2. We have to turn on 3 and 2, sir.
We have to turn on 3 and 2. What is the startup cost for unit 2?
600, sir. For unit 2.
2 is 100. What is the startup cost for unit 3?
100, sir.
So, to move from unit state 1 to state 2, we have transition cost 700. State 1 to 3, transition cost is 600. 1 to 4, transition cost is 700. So, similarly, for every transition, there will be a cost associated. Okay. So, you can see that here the transition cost is mentioned as 0 because in this state all the generators were running. To move to this state, you have to turn off the third generator. Shutdown cost is not given. So shutdown cost generally may not be given. We will assume that it is 0. So the transition cost is 0. So each transition have a cost, and each state have a fuel cost. Each transition have a startup cost. Each state have a fuel cost. Now, to supply the demand 150 megawatt, 300 megawatt, and 200 megawatt. There are several possible paths to be followed by your generator. This may be one path. This may be the other path. The other path, the third path may be like this. The fourth path may be like this. The fifth path may be like this. Okay. So we can move from state 1, state 4, state 7. 1 to 3 to 7. State 1 to 2 to 7. State 1 to 2 to 6. Then state 1 to 2 to 5. Okay. These are all the possible paths. Now we find out the total cost for all possible paths. And the lowest total cost is the optimum. You can find out the probable cost for all possible paths. For 3 paths, I have given the values. You can find out the cost for each state and the transition cost. You add the cost for each state, that's the fuel cost and the startup cost associated with all paths, and the lowest cost path will be the optimum. Lowest cost path will be the optimum. Okay. So this is the optimal solution for our problem. Okay. So we can go to state 1 to 2 to 5, which incurs $7,500. So to obtain the optimal unit commitment schedule, we determine the feasible units combination in each load interval. Then we obtain the feasible transmission paths. Okay. After that, determine economic dispatch in all states in the feasible path and find the fuel cost. Then we can calculate the total operating cost for each part, fuel cost plus startup cost. The path corresponding to the least operating cost is the optimum. This is a technique which is based on dynamic programming. We enumerated all the parts, all feasible parts, and from the feasible parts, we can find out the optimal path, optimal unit commitment schedule we can calculate. Now, this is not a solution technique exactly based on the dynamic programming. It's a mixture of dynamic programming and exhaust enumeration technique. The technique have these many steps. We will determine the feasible combinations, dispatch them, and we will find out the startup cost and fuel cost at all the routes and nodes in the path, and then we will select one optimal unit commitment schedule or one unit optimal path. This can be similar to your shortest path algorithm you would have studied in your data structures. Okay. Now, I hope you have understood it. You can look into what is dynamic programming and how that can be applied to payment commitment problem. And I will be forwarding you the assignment. And you can submit it on 22nd of October. And also the slides will be given to you. You can use them, solve the assignment, and submit it on 22nd. If you have any doubts, please let me know.